you last time. Okay, yesterday. So we are having a problem because our wave function is not continuous across the potential. Clear? So because we are having a singularity due to this delta function. Okay, what we will do? We will simply regularize this thing. Okay, so let me define this delta function. Okay, this way. So this is our potential. So you are having at t equal to 0. So what I am doing, so I am simply approximating this delta function as certain function within this very range. Clear? Okay. So that means okay. So you can think it as simply as the sum of the rectangles. So you take the sequence of the rectangles, let's say of the decreasing size, such that when you take n tends to infinity, so the area under that curve will be 1. Got it? Okay. So this is how I define it. So, like this. Okay. And 0. Clear? So this is how I regularize. Okay, so the reason being, so this is one way to do regularize the delta function. So there are another ways. So you could have equally written, let's say, delta function like this thing, this object, let's say epsilon by, let's assume t square plus epsilon square, okay, 1 by pi, okay, for epsilon tends to 0. If you take epsilon tends to 0, this very function goes as a delta function. Clear? So this kind of curve is like this thing. So it is simply a Lorentzian curve, not the Gaussian curve, it is the Lorentzian. Okay? So when you take epsilon tends to 0, so this width will decrease and the height will increase. Clear? So it will tend to be a delta function. Okay, so why we are not using this kind of regularization? Why we are using this regularization? Okay, since we are dealing with the sudden perturbation. Clear? Got it? So so this is some sort of a smooth curve. Clear? So it is having a well defined width, this kind of curve. Clear? So that's why I will not use this. There is another regularization as well. So you can equally put it in terms of the sine function. But we are dealing with the sudden perturbations. This kind of regularization is okay. Got it? So let's say it would have been like this kind of perturbation. Let's say okay, so this potential goes to infinity somewhere, but you are having a well-defined range within that very range. So then you can equally define it by some sort of smooth curve. Clear? Clear? Okay. So now let's use this kind of okay. So now what are our boundary conditions based on this? Okay. So based on this thing, what I am having, so I'll be having this CA when you are having T as minus epsilon. Okay, so that means on this very region, 0 minus region. Clear? So what it will be? So it is equal to 1. Clear? So now what you are having CB at T equal to minus epsilon, that's equal to 0. Okay, so now if you are having CA, T is equal to plus epsilon. So what that is equal to? No, it's not equal to 0. So it will be simply equal to A because the wave function we started with. So in the region 0 plus region, we start with this kind of wave function. Okay, clear? So you are having the state vector in this very domain. It will be simply the linear combination of these two states. Clear? Okay. And what you are having then? CB as T. So it is simply equal to B. So these are the boundary conditions, and now within this very domain, minus epsilon to plus epsilon, you are having CA and CB are governed by these kind of equations. Okay, so that means within this region. Okay, so within this region, let's say, so I have it is not correct. So like this thing, so we are having these equations I and cross C dot AP. Okay, so what you are having? E raised to I omega t alpha. What is our delta P now in this region? It's 1 by 2 as epsilon So you are CBT, and then you are H just C dot B T. So it is e raised to minus I omega naught alpha star 1 by 2. Okay. Clear? So now the delta function is removed. Now when we end up the calculations, when we try to figure out what is the probability of figuring out our state, if it initially started in the state A and now the state has made a transition to the system has made a transition to the state B, and calculating that probability, okay, so then at the end we'll put this epsilon tends to 0. Okay, so the important point is when you regularize the delta function or any kind of function which diverges at certain point, when you try to regularize that kind of function, at the end of the calculations you should get actually the finite calculation. When you remove that regularization parameter, you can think this parameter regularize this delta function. Okay, so when at the end of the calculation you need to put actually epsilon tends to 0, because we don't have this finite domain, this minus epsilon to plus epsilon. Clear? We are having actually it is sharp t equal to 0. Got it? Okay. So now what we will do, just to solve these two equations, how to do it? So the easiest way, just differentiate the first step. Okay, so you will get actually C double dot, then the differentiation of this thing, then okay this as such, plus the other term, keep this as such, and the differentiation of this thing. And C dot B is this. Okay, got it? So let's do this thing. So I will skip that step. So let me write. Or you can do this thing, this as well. So so let's do the differentiation. So let's differentiate this thing. So it is C double dot dt. Okay, so that's equal to minus I omega naught e raised to minus I, like this thing, alpha star by twice epsilon CET. Okay, plus e raised to minus I omega naught t alpha star by twice epsilon C dot A. Clear? So now use C dot A from the above equation. We will get this equation. So, like this is the equation I will get. Okay. So this is the second order differential equation. What I will get for CT, or you can equally start with the C double dot A. For CA you can also get it. So if I know, okay, so from this equation I will figure out the solution CB. Clear? So if I know the CB, so that I can substitute here, or I can substitute it here, get CA, because they are coupled. So this is the consistency check. So if you try to convert this into a second order differential equation, you will get the solution corresponding to CB. Clear? And a consistency check, if when you have to figure out what is CA, then you need to plug this solution back here to figure out CA, such that the probabilities has to be, sum of these probabilities has to be equal to 1. Okay, so this is the consistency check. Now, how to solve this second order differential equation? You start with some arbitrary solution. Clear? So for a second order differential equation, an exponential is a good choice. Okay, so start with. Okay, so let me write this CB. Okay, so let's CB of t is equal to, so I will not choose a normalized one, so that doesn't suffice. Let's choose this CB of t is equal to lambda t, where lambda is unknown to us. Okay, so substitute here. So what you get? So you get lambda square minus I omega naught lambda plus mod of alpha square by twice epsilon h whole square, that's equal to 0. So from here you get lambda actually. Okay, so let's calculate this lambda. Okay, so calculate lambda. What is lambda? So lambda will be simply equal to I omega naught plus minus. Okay, so minus b plus minus root of b square minus a square. A square. Constant में अगर miss, okay, minus a mod of alpha square divided by epsilon h plus whole square. Minus 4ac है, that 2 square will cancel out divided by 2. Okay, so this I will write simply lambda is equal to I omega naught by 2 plus minus I omega by 2, where this omega I can write root of omega naught square plus mod of alpha square. Clear? Okay, so these are the complex roots. Now let's calculate our CB. So what is the solution? Okay, see, since I am having two roots, okay, so these, okay, so what will be the solution? Now tell me, anybody? How I will write the solution? How I will write the solution? Simply. So if you know the roots of the equation, how you will write it? So CB of D will be simply A e raised for, okay, the first one. Okay, so let's write lambda plus minus. So it is lambda plus T plus B e raised for lambda minus T. Clear? So how much is that? A. So lambda plus both contains e raised for I omega naught by 2. So you can take it out. So it's e raised for I omega t by 2 plus b e raised for minus I omega. So is this a solution? Clear? Okay, so now what we have to apply? So let's apply the boundary condition. So what is our boundary condition? CB at t equal to minus epsilon, that's equal to 0. Is it true? So there is no CB on the left of the potential. So that's equal to e raised for, okay, I omega, okay, so minus omega epsilon by 2. So it is a e raised for minus I omega epsilon by 2 plus b e raised for I epsilon by 2. Clear? So you got therefore, which implies a e raised for minus I by 2, that's simply equal to minus b e raised. So you have got a in terms of b or b in terms of a. Clear? So you can write therefore, which implies CB of t is simply equal to e raised for I omega naught by 2. So a you will take out. Okay? So you will put b or a. Okay, so let me write a. So what it is? E raised for I omega. B will be minus a. So it is simply e raised for minus I omega epsilon e raised for minus omega t. Clear? You sure? Got it? Okay, so now you can calculate now CAT. So you have, so what I have to calculate now? A is this constant I need to figure out. Okay, so now you calculate CA. How you calculate CA? Anybody? So from that differential equation CA of B, so you are having C dot B is equal to something that I will put in this form. So it is twice I epsilon H cross divided by alpha star, okay, e raised for minus omega t C dot B of t. Clear? C dot B is like this thing, huh? So I have written as CA. So substitute here. So what you will get CA of t as, okay, so it will be simply epsilon H cross alpha star e raised for minus I omega t by 2. So A is there, okay, so it will be simply omega plus omega naught kind of, okay, omega minus omega naught. So this is what you will get. So so there is, yes, wait a second, yes, it's okay. Clear? So this is CAT. Everybody followed it how I got? Huh? Everybody followed it? Okay, good. So now what is the condition? CA at t equal to minus epsilon, what is that equal to? A. Or you can call equal to 1. At minus epsilon, I should have put that 1. So that is 1. Only at t equal to plus epsilon, that's A. Clear? So let's put it. So use this boundary condition, you will get, so epsilon h cross by alpha star a raised power minus I omega. So it will be simply plus epsilon by 2 a omega plus omega not a raised power minus I omega epsilon by 2 plus omega minus omega naught e raised power I omega epsilon by 2. So now you got, actually you will get a solution for a here. Clear? So this object is equal to 1. So which gives me a. So let me write the value of a. It's simply alpha star divided by twice epsilon h cross omega e raised power I omega minus omega naught epsilon by 2. So this is the value of a. Okay, substitute now. So you have got now CA as well as what? CB. Clear? So this I am going, okay, quickly in a sense, because this is a simple manipulation. Okay, I am just giving you the idea how to manipulate things. Okay. So now let's substitute in this very equation for A. Okay, because A is unknown to us, A we have got. And also in CAT, A is unknown, you will plug in this A. Clear? So that we'll get CA and CB. Okay. So we have applied only boundary one side of the boundary. Clear? At minus epsilon. Then we will apply for the plus epsilon. Okay, so therefore I can write this CA of T. So it's equal to e raised power minus I omega T plus epsilon by 2. Okay, so it will be simply cosine of omega T plus epsilon by 2. Okay, plus I omega naught omega sine of omega T plus epsilon by 2. Okay, so you need to work it out. So when you put a this factor here, okay, so then you have to work out these exponentials. Okay, so you have to put it in terms of sine and cos. So that's why I have put it directly here. Similarly, you will get this CB of T. Okay, so it is minus I alpha star divided by epsilon h trans omega e raised power I omega T minus epsilon by 2. Okay, sine of omega T plus epsilon by 2. Okay, so you have got now CA and CB. Let's apply the condition. So we are having this CA T is equal to plus epsilon, that is simply equal to A. Okay, so now let's apply. At T equal to plus epsilon, so it will be twice epsilon, so it is simply omega epsilon, and so what you will get? E raised power minus I omega naught epsilon cos of omega epsilon plus I omega naught by omega sine of omega. Clear? So what will be B? So that is CT T is equal to plus epsilon, so that is simply equal to B. It will be minus I alpha star epsilon h plus omega. So this will be 0. Sorry, so this will be 0. It is 1 there. So it will simply sine of omega epsilon. Clear? Got it? Okay. So now, so this is forward when you are having finite epsilon, although it is an infinitesimal quantity. So now let's take epsilon tends to 0 limit. Okay. So what you will get? Anybody? Okay. So let's look at this very thing. So you are having omega. What is omega? Now let's. Okay. So what was omega? Omega is root of omega naught square plus mod of alpha square divided by epsilon h cross whole square. Clear? Got it? Okay, so now let's take the limit. Okay, so let's take the limit epsilon tends to 0. What will happen? So when epsilon tends to 0, so this quantity is very large, is it? Got it? So I can ignore this omega naught. So that means this omega tends to what? So it will be simply mod of alpha divided by this epsilon h cross. Got it? Samashyaman? Okay, so now let's take epsilon tends to 0. When you take epsilon tends to 0, this term is gone. So this will become 1. Now what about this omega epsilon? What will be omega epsilon? No. Omega into epsilon, it will be alpha by h cross. Got it? Now what about this thing? What about? Because there is an omega sitting in the denominator, clear? So omega is inversely proportional to epsilon, so it will become, okay, so let me write this thing. So let's put this. So you are having CA t equal to plus epsilon, so that's equal to, or in other words, okay, so let me write A. So A is equal to e raised power minus I omega epsilon, okay, cosine of, okay, so let me write it as such. So I omega, so I should put epsilon tends to 0. Okay, so I should have put epsilon tends to 0. This thing. So epsilon tends to 0. This A becomes as, so exponential become 1. So this will become cos of omega epsilon is what? Simply mod of alpha by h cross plus I omega naught. Omega is what? So it is something mod of this thing. So it will be epsilon h cross sine of. So this will be simply mod of h cross. Clear? So this will become 0. So or I can write simply A is equal to cosine of mod of alpha by h cross. So now you see A is independent of time. Clear? So what we predicted earlier. Okay. Similarly, let's take B. So therefore, also, what about B? So B is this very quantity. So it is minus I alpha star. Epsilon omega is what? So it is something mod of alpha. So h cross. Clear? Okay. So then sine of mod of alpha by h cross. Got it? So now let's write. I mean the complete solution what we have got. So everybody followed it? Okay. So now we are having a finite result. Okay. So if it would have been, let's say infinite, either the regularization what we have done that is wrong, or there are some problems with the problem itself. Okay. Got it? This regularization is sometimes known as introducing the cutoff in your problem. So limiting the domain means introducing the cutoff. Okay. So this will be frequently used in quantum field theory. Okay. So now let's write the CA of t. Okay. So we are having here for the CA of t. So this I can write as 1 when you are having t less than 0, because t less than 0 means t equal to minus infinity or t equal to 0 minus. So on the left of this potential. Okay. So here you are having system governed by h naught. What was our initial condition? So we said system started in the state A, and we have to figure out what is the probability that it undergoes a transition from A to B. Clear? So that's why I have put it as CA equal to 1. So here I will be having this as cos of alpha by h plus when t greater than 0. Okay? Got it? समझ आया? Yes. So now what about the CB of t? So initially it is actually equal to 0, because our system starts in A. Okay. Here what you are having minus I alpha star by magnitude of alpha sine of alpha by h plus. Clear? Sorry. So what it will be? So it will be simply root of this thing. Yeah? Will it be root? Huh? So t greater than 0. Okay, so what it will be here? What is this alpha star by magnitude of alpha? So can I write it? So it is. I can write L. Okay. Let's write it this way. So there is. Okay. So now what we need to calculate? We have to calculate probability. Okay. So we have calculated actually this psi of t at any time. CA of t A plus CB of t. This we have calculated now. Clear? So now what is our probability? So probability of transition from A to B. So that's simply mod of CBT square. So how much is that? So it is simply sine square mod of alpha by. Got it? Is everyone now so much? Any problem? Okay. So that, okay, so now if you can work it out, mod of CA square is cos square, huh? Sum total of probability should be equal to 1. That is true. Cos square plus sin square, that is equal to 1. Got it? Any question till now? So if you have any problem in perturbation theory, just ask. So because this ends our perturbation theory, huh? So you can relax, you can have a sigh of relief. Huh? Any question? Any problem? Where? So this is the psi of t is the solution for the time dependent Schrodinger equation what we are trying to solve. Clear? So what were unknowns in that? CA and CB. Clear? So we have figured out CA and CB. Okay, so mod of CB square will give you the probability for finding the system in the state B. Mod of this square, CA square, will give you the probability of finding the state in this state A. Got it? And the sum total probability should be equal to 1. So mod of CA square plus mod of CB square is equal to 1. Got it? Okay. Okay, so let's do something new now. Huh? Okay. So we'll be doing now scattering. Okay. So we'll start with the simple things, then complicate the business. Okay. So what you mean by scattering? So let's start from you. So when you say scattering, you have done it in the classical mechanics. Okay. So what do you understand by scattering? What is the, okay, so let's put the question this way. What is the basic idea of scattering? Just start from you. Any idea? Okay, so the basic idea is, if you want to know about something, okay, if you are in an objective, unknown objective, and you want to know about that objective, okay, so how to do that? How you can gain information about that objective? Clear? So you throw on that objective, you throw something on that objective, and this something will bounce back from that objective, okay, and it will carry the information, and you get all the information from this something which has bounced back from this object. Clear? So this is the basic idea of the scattering. Suppose if I need to know you people, okay, let's say if you are let's say if I have to see you, so I need to throw light on you, and it gets scattered. From that scattering, okay, what you call the reflection, okay, so I get the idea how you look. Clear? So this is the basic idea of the scattering. But in quantum mechanics, you are okay. So so let me put this way, in classical mechanics. So there are limits on that scattering. Okay. Let's say if you are having this hard wall. Okay. So let's say if you are having a thin wall, thin barrier. Okay. You threw some object. Let's say with the slow speed, it will bounce back. It will not penetrate the wall. Okay. But if you threw it hard enough, so it can go through that barrier. Clear? Okay. So it can penetrate through that barrier if the barrier is small. Okay, so you have to okay, so the other way. But in quantum mechanics it is entirely different. You are having both the reflection as well as the there is a concept of the tunneling through the potential. Okay, so that we call the, okay, we'll call it a transmission here. So even if you are having the low energy particles, so they go scatter through the barrier, there is a finite probability that you can have a transmission through that barrier. So this is a very peculiar property of the quantum mechanics. Clear? So let's try to explore these things in detail. So let's go first with the one-dimensional case. So let's look at the quantum mechanics in one dimension. Okay. So let's consider, since we will be dealing only with the potential scattering. So let's say fixed potentials, the potential which does not change at all. Okay, let's think of you are having the hydrogen nucleus, clear, and you are hitting it by some external particles. Okay, so let's say the Rutherford kind of scattering. You see essentially that nucleus, the potential of the nucleus remains constant, clear? And that kind of scattering, I mean the stationary collision theory we are trying to understand here. Okay, then we'll go to time dependent phenomena. Although time dependence is intrinsic to it, but we will not consider that okay, explicitly. So let's consider a potential somewhere. Okay, let's say some potential which is a regular function. Okay, so let me consider a particle that's moving in one dimension. Okay, and it hits the potential somewhere. Let me put about this potential for which we are trying to gain information. Okay, so let's put some restrictions on this potential. This potential vanishes at plus minus infinity. Let's say it goes to 0 at x equal to plus minus infinity. Okay, so it's a regular potential, and I say there are no divergence for the time being, and there are no discontinuities in the potential. Okay, so we can take discontinuities. Let's not take the I mean singularities in the potential. Okay, so let's say it is a regular function kind of thing. Let's say it is like this thing. At infinity it goes to 0, so that means, so it is localized somewhere. Got it? So I am considering this as a localized object, yeah? Localized potential. Think of the hydrogen atom. What is the form of the potential? It's 1 by r. So it falls off to 0 as you move to larger distance, x to plus infinity. Yeah? There is no minus infinity, but it goes to 0. Clear? So, but in case of the harmonic oscillator, that is not true. Harmonic oscillator potential grows as you go to x to plus minus infinity. Those potentials I am not considering here, although that's also a smooth potential. But I will I'll tell you later on about those potentials. I will simply consider this kind of potential. Okay, and let's say you are having a particle coming from left and going through, hitting this very potential. Okay, so how to solve? Okay, so in one dimension, but okay, so for this kind of problem, if I have to solve for we have to solve the Schrodinger equation for this case. Okay, so let's write the Schrodinger equation. So in one dimension, that's equal to E psi, because I'm not considering the time dependent phenomena. I'm simply considering this as the stationary kind of thing, time independent Schrodinger equation. Okay. So now this equation admits solutions for this kind of potential. Okay, so there exist actually two types of solution for this potential. Okay, so first we call as the bound states. Okay, so I will use the terminology the asymptotic limiter. Asymptotic limit means so this potential falls off at the larger distance to 0. Clear? So we are having two types of solutions to this very problem. Okay. So what are those solutions? The first solution is the bound states. Okay, so bound states we call those states which are localized in space. Okay, so these are the localized in space. Any more property to this thing for the bound states? Okay. Huh? So one important property for this, because we have to describe them by the wave functions, clear? So the wave function or the energy eigenstate must fall off to zero in the asymptotic limit. Clear? So this is very important property of the bound state. So I can say the wave function must go like this. Lambda is some arbitrary parameter, and okay, and you are hanging. So it is x goes to plus minus infinity. It is because of this very potential, nature of this very potential allows us to, the potential which I am saying, okay, this kind of potential, it allows us to have the bound state wave function to fall off exponentially. Got it? Okay, so now if I write this kind, okay, so this is a very general solution. So you can choose this lambda as by the condition of the problem. Okay, so let me give you an example. Let's say in 3 dimensions you are having the hydrogen atom. Okay, potential is what? Okay, minus 1 by r. Clear? So what is the wave function, ground state wave function? So it is something e raised power minus r by r naught. Clear? Where r naught is the Bohr radius. Clear? So this wave function falls off to 0 as r tends to plus minus infinity. Clear? Rather r tends to plus infinity, because we don't have minus infinity in the hydrogen atom. Got it? You are because it starts from 0. Radius starts from r equal to 0 to infinity. Got it? That's why we have to look in the one side of the region. Okay, so now let's look at so what is the energy for these very bound states corresponding to this kind of potential. Okay, so you can plug in this this wave function here, and in the asymptotic limit, okay, since I'm having the asymptotic limit, v goes to 0. Okay, so it implies this energy has to be minus extra square lambda by 2m. Is that true? So you just substitute here. So what you will get? So minus extra square by 2m. It is the double differentiation of lambda, this wave function. Okay. So this term will go to 0. E will be this value. So that means for these bound states, so E has to be less than 0. Okay. So one important point is, so if there is no potential at all, okay, first point is that, so these solutions are actually normalized wave functions. When I am saying they are localized in space, so that means I can normalize these very solutions. Okay. So one important point is here, if I remove the potential, if the particle is free, completely free, okay, so then the wave function will not go to 0 either at x equal to plus infinity or at x equal to minus infinity. The reason being, let's say, even if the wave function goes to 0 on one side, let's say, if you are having the wave function like this, let's assume, so at x tends to plus infinity, it goes to 0. But if you stretch it to x equal to minus infinity, it increases. And the other way around, if you take it plus at x equal to minus infinity, it will go to 0. But at x equal to plus infinity, it will go up. It will blow up. Got it? So those solutions are non-normalizable solutions. Got it? Okay. So it is actually the potential helps us to normalize these various solutions. Got it? So let's say if you are having simple free particle without any potential, you are having only the plane waves, and you are not able to normalize those solutions. Okay? So the nature of the potential helps us to normalize these very wave functions. Let's say if you are having a particle in a box, you are having a potential that is 0 within a finite domain. Clear? So potential is 0 and rest it is infinity. Okay, it is 0. I mean, you are having simple barriers. Potential is there, although it is 0. Got it? And that simply gives you the normalizable solutions. Got it? Okay. So for these normalizable solutions, what I am saying? So we are having the normalizable solutions. It is because of this very potential. So what I am missing somewhere? Okay. Yes. So because of this condition, you are having these localizable solutions. You can choose this lambda. Okay, depending upon how depending upon the behavior of this very potential, you can choose this lambda. Okay, so if you choose this lambda, let's say it can be it can specify the quantum number. Okay, so in such case you will be having the discrete energy states. Okay. Okay, so when you are having such kind of behavior, as for the bound states, you will be having always the discrete spectrum. Got it? समझ आया? Okay, so here this kind of analysis is true for these kind of potentials, but in general potential, this analysis hold. Okay, so the bound states hold for this thing. If you are having, what is the u at plus minus infinity? Got it? So in general, the bound states will be like this thing. If you are having, let's think of the harmonic oscillator. Got it? What is the potential at infinity? It grows, it diverges because it is x square. So how you choose the bound state? The energy must be smaller than the potential at plus infinity and potential at minus infinity. Got it? So look at the particle in a box. Okay, so potential, what is the potential? It is infinity at the ends of the box. Got it? So the energy is always less than that. Okay, let's take whether this holds for this analysis or not. Let's take the potential goes to 0 when x tends to, okay, so this tends to infinity. So this is 0, this is also 0. Got it? So then you are having energy less than 0. Got it? So this is a very general condition. Okay, so this is all about the bound states. Okay, so now let's go to the another solution. So you are having this kind of potential will admit two types of solutions. One we call the bound states, another we call as the scattering states. Okay. So these are not localizable, not localized solutions. Okay, got it? So when you say they are not localized, so that means when you, okay, so localized means what? So that is the condition, they should fall up to 0 as you in the asymptotic limit. But when you go into the asymptotic limit, so what will happen? So they are essentially actually free. So there is no potential. So when I am saying potential, let's say you are having this kind of potential, what I have drawn here. So this go, okay. So I should have put in another peak like this. Okay. So you are having this as the potential. So here, so this is the asymptotic limit. Let's say, so you don't have the potential here, you don't have the potential here. Got it? Because it vanishes. So when you don't have the potential there, when I am saying the non-localized solutions, that means what? The particle is essentially free. When you are having a free particle, it is always represented by a plane wave. And the plane waves are non-localized states. Got it? Okay. So how I can write that? So then I can be having this kind of possibility can arise. You are having a plane wave that can move from left to right, or you can be having a plane wave that is moving from right to left. Got it? So in general, we write these non-localized states as this thing. These are the plane waves, where k is the momentum. Huh? Okay, so let's put it in the, the Schrodinger equation. Okay, so you can have like this thing, minus h square by 2m d2 psi by dx2. Okay, plus v psi is equal to e psi. Okay, since v goes to 0 in the asymptotic limit, so you just differentiate it. E will be simply equal to h square k square by 2m. So it means, so you are having for these scattering states, energy is always positive. Got it? समझ आओ? So psi, you are having, you have to double differentiate it. It is minus, sorry, it is I square. Whether it is minus I square or plus I square, that's minus. Minus and minus is plus. It is h plus. Okay. So for the scattering states, energy is positive. Okay, it cannot be negative. Got it? So in which condition? When you are having the potential that falls off asymptotically to 0. Got it? Now let's say if you are having the potential that does not go to 0 asymptotically. So still energy has to be greater than what is the potential at infinity plus minus infinity. Got it? Or at the larger distances up to which the potential is defined. Got it? So the energy should be larger than that. Rather, always energy has to be positive. Okay, for positive energy solutions, you will always get actually the scattering states. Huh? Okay. So you should not confuse. Let's say for the harmonic oscillator, energy is positive. So for you should not confuse yourself. Okay, so, let me clarify this very point. So let's take the harmonic oscillator. Okay. So what is the potential? It is x square. Got it? So what is the energy here? So it is n plus half h cross omega. So this is always positive. Does it mean it's a scattering state? No. So what is the condition for the bound state here? So in this case, the condition for the bound state is E has to be less than what? U at plus minus infinity. Got it? Okay. Okay, so let's take similarly the particle in a box. Okay, so when you are having particle in a box, what you are having potential? Potential is 0, but that is infinite at the ends. Got it? Okay, so what is the energy? So energy is also positive here. So what is energy? So that's n square pi square extra square by twice ma square. That is positive. Clear? So but this condition does not hold here. So your energy has to be less than this infinite limits. Got it? And what is the behavior of the potential at the asymptote? Got it? Okay. But in that case, when you are having the potential that goes up to 0 in the infinite limit, okay, when at the far off distances, the scattering state is always having what energy? Positive energy. Okay, you can even in this case. Okay, so we will consider, let's say, step L potential. Okay, as step potential we will consider. We'll take the energy positive. Got it? So for scattering states, energy is always positive. But for bound states, the energy will depend upon how you choose the bound state. Got it? What is the what kind of potential you are having? And these scattering states are always represented by these plane waves. Okay? So because these are not normal, you cannot normalize these plane waves. Okay, you can have only the normalization of these plane waves in a finite, let's say, space. What we call it the box normalization. Got it? Okay. So let's move ahead. So I will be having this kind of, okay, so from this understanding, I will be having these waves, let's say e raised power I kx. Okay, so since k is positive, okay, so you can calculate k here. So you will be having k as, just remember this formula, h square. So I will call this as right moving wave as e raised power I kx. So because k is positive, so this wave will be going from left to right. Okay, so that's why I put it as a right. So it's a right moving wave. And you will be having another possible solution, a left moving wave. So left moving wave means it has come from right to left. So in other words, this e raised for ikx, you can put it here. Let's say you are having e raised for ikx, it goes in this direction, and e raised for minus ikx, you can put it in this direction. These are the two possible solutions. Got it? Okay. So let's move ahead. So we have defined these kind of states. Four. So let's stop here. Then we can.